Imagine a place in the universe where time itself starts to twist, where light bends so hard it never comes back, and where the laws of physics, the ones that built our phones, rockets, and satellites, quietly stop working. Now, imagine you are falling toward it. There is no scream in space, no wind, no impact, no sound of rushing air. Just the silent pull of gravity growing stronger with every second as a dark circle on the starry canvas slowly widens in your field of view. Around its edges, light stretches into a glowing ring, like fire wrapped around a hole in reality. Astronomers have a precise name for this region: the event horizon. Everyone else knows it by something simpler: a black hole. From far away, it looks like nothing more than a shadow, a circular absence carved into the fabric of space. But that shadow marks the border of the strangest place we know. Cross that invisible line, and even light cannot escape. Cross that line, and you are no longer just falling through space, you are falling through the rules. For a long time, black holes were just an uncomfortable prediction on paper, born from the same equations that describe gravity on Earth. Even Einstein himself wasn't entirely happy with them. The idea that matter could collapse into an infinitely dense point, a singularity, felt less like science and more like a warning that the math had gone somewhere it was never meant to go. And yet, the universe did not ask our permission. We now know that black holes are real. We have watched stars orbit an invisible monster at the center of our galaxy. We have seen for the first time the glowing halo of hot gas swirling around a dark circle in another galaxy, captured by telescopes spread across the Earth. We have listened to space-time ring like a cosmic bell when two black holes collide. We know black holes exist. What we don't know is what happens inside. The closer you fall toward the event horizon, the stranger things become. Time for you ticks normally. Your heart beats, your thoughts flow. But for someone watching from far away, your fall slows down, as if the universe is pressing pause. Your image stretches, redshifts, fades. You never seem to cross the border at all. From their point of view, you simply freeze on the edge of the void. From your point of view, you keep going, past the bright ring and into the darkness. Inside, our best theories fall apart. Gravity becomes so strong that our equations explode into infinities. Quantum mechanics, the rules that govern atoms and particles, refuses to cooperate with Einstein's smooth fabric of space-time. Somewhere between the horizon and the singularity, our understanding of reality tears like thin paper. In this episode, we are going to the edge of that tear. We will explore what black holes are, how they form, and what happens the closer you get to their one-way door. We will walk into the paradox that made Stephen Hawking rethink the very idea of information. And we will follow the clues that suggest black holes might not just be cosmic trash cans, but crucial players in the story of galaxies, stars, and maybe even the birth of the universe. This is not a journey with clean answers. It is a journey into the places where our laws of physics break down, and where our curiosity is forced to step in and ask the oldest question in science. When the math stops working, what is really going on?
To understand why black holes are so strange, we have to start with something familiar: gravity. For most of human history, gravity was just things fall down. Apples drop, arrows arc, planets move across the sky in patterns we can predict. Isaac Newton turned this into precise mathematics in the 17th century. For him, gravity was a force between masses, acting at a distance. The bigger the mass, the stronger the pull. Simple, powerful, and incredibly accurate. Then came Albert Einstein. Instead of treating gravity as a mysterious force, Einstein described it as geometry. Massive objects don't pull on things directly. They bend the fabric of space and time around them, like a heavy bowling ball placed on a stretched rubber sheet. Smaller objects simply follow the curves in that sheet. They are not being pulled. They are just moving along the straightest possible paths in a warped landscape. Most of the time, this picture works beautifully. It explains why Mercury's orbit wobbles, why light bends around the sun, and how the universe expands. But when you push Einstein's equations hard enough, when you cram too much mass into too small a space, something dramatic happens. The math predicts that a star much more massive than our own sun, after burning through its fuel, can no longer support itself against its own weight. It collapses. First, it shrinks into a dense core. Then, if the mass is high enough, even the pressure of atomic matter cannot resist the crush of gravity. The star keeps falling inward, past any familiar form of matter, toward a point of infinite density, a singularity. Around that singularity forms a boundary, the event horizon. Not a solid surface, but a radius in space where escape becomes impossible. To get out from inside that radius, you would need to move faster than light, and nothing can do that. The horizon is therefore a one-way door. Cross it, and all paths lead inward. What makes this even more unsettling is that the horizon itself is deceptively ordinary. If you are falling in and the black hole is big enough, you might not notice anything special as you pass that point. No bright flash, no physical barrier. Space-time around you simply continues to curve more steeply. Your fate is sealed, but your senses might not know it yet. Meanwhile, for an outside observer, you never quite get there. As you approach the horizon, time dilation stretches your final moments. Your signals take longer to escape, your image slows, reddens, fades, and finally vanishes, frozen forever on the border, from their perspective. Two stories of the same fall, both predicted by our best theory of gravity, and yet the problem is just beginning. Because as you get closer to the center, Einstein's smooth fabric of space-time is forced to curve more and more sharply, until, in the equations, it tears. Values like density and curvature blow up to infinity. In physics, infinity is not an answer. It is a flashing red light that says, here, your theory has reached its limit. At that same scale, another set of rules refuses to stay quiet: quantum mechanics. It governs atoms, particles, radiation, everything happening at the smallest scales. General relativity and quantum mechanics are the twin pillars of modern physics. Each works flawlessly in its own domain, but inside a black hole, they're forced into the same room, and they start to disagree. In that disagreement lies one of the greatest mysteries of our time. Not just what is inside a black hole, but a deeper question. How do you describe a place where our two best descriptions of reality cannot both be true?
The first cracks in our understanding of black holes did not appear in a telescope. They appeared on a blackboard. In the early 1970s, Stephen Hawking asked a simple, dangerous question. What happens when you add quantum mechanics to a black hole? If empty space is buzzing with virtual particles that pop in and out of existence, what does that quantum foam do near the sharp edge of an event horizon? The calculation that followed changed everything. Hawking discovered that black holes should not be perfectly black. Quantum effects at the horizon allow them to emit a faint glow of radiation, now called Hawking radiation. Over enormous spans of time, this slow leak causes a black hole to lose mass, shrink, and eventually evaporate completely. At first, this sounded almost poetic. Even the darkest objects in the universe are not eternal. But then came the problem. Imagine you throw something into a black hole: a rock, a book, a person. According to quantum mechanics, information about the state of that object, its exact structure, its quantum configuration, can never be truly destroyed. It can be scrambled, spread out, hidden beyond practical recovery, but not erased from the universe. Now combine that with Hawking's result. If a black hole can completely evaporate away into a featureless mist of thermal radiation, what happens to the information about everything that fell in? If it is gone, quantum mechanics is wrong. If it somehow leaks out encoded in the radiation, our understanding of black holes is incomplete. If it remains trapped in a singularity that no longer exists, both pictures seem to break. This is the black hole information paradox. Over the decades, physicists have proposed escape routes. Maybe information is stored on the horizon itself, like data on a cosmic hard drive, an idea connected to something called the holographic principle. Maybe space-time rearranges itself so that what looks like destruction from one vantage point is just an extreme kind of scrambling from another. Then, in the 2010s, another twist appeared: the firewall paradox. Some researchers argued that to preserve information, the horizon could not be the smooth, harmless region that general relativity predicts. Instead, it might be a searing wall of high-energy particles that would instantly burn anything trying to cross it. That solves one problem, but creates another. It breaks Einstein's picture of a peaceful fall through the horizon for large black holes. Smooth horizon or quantum firewall? Information lost or preserved? Our theories circle the event horizon like light itself, bending, stretching, almost escaping, but never quite getting free. Outside the equations, the questions become even more unsettling. What does it mean for information to be destroyed if no one can ever get it back? Does the universe care about the details of a book or a brain that fell into a black hole billions of years ago? Or is the real issue not the fate of individual objects, but the consistency of the rules that apply to everything? At first glance, these might sound like abstract puzzles, but they point to something profound. Somewhere beyond the horizon, or perhaps on it, there must be a deeper layer of physics that we have not yet seen. A theory that unites gravity and quantum mechanics into a single language. String theory, loop quantum gravity, holographic dualities, emergent spacetime. Behind each of these complex ideas is the same simple question: what really happens to reality when it crosses the point of no return?
While theorists wrestle with paradoxes on the chalkboard, the universe continues to do what it has always done. It makes black holes. Some are born quietly from the deaths of massive stars. When such a star exhausts its nuclear fuel, its core collapses and its outer layers explode in a supernova. If the core is heavy enough, no known force can stop it from falling inward beyond its own event horizon. What remains is a stellar mass black hole, only a few tens of kilometers across, but with a gravitational pull so intense that not even light can escape. We do not see these black holes directly. We infer them from their influence on their surroundings. A star orbiting an invisible companion that is too massive, too compact to be anything else. Hot gas spiraling into darkness, heated to millions of degrees and pouring out X-rays before it crosses the point of no return. These are the fingerprints black holes leave on the cosmos. On a much grander scale are the supermassive black holes. These monsters sit at the centers of galaxies, including our own Milky Way, with masses millions or even billions of times that of the Sun. How they grew so large, so fast, is an open question. We do know they dominate their neighborhoods. Stars whip around them at incredible speeds. Entire disks of gas and dust swirl under their influence, sometimes lighting up as bright as 1 trillion suns when material falls inward. For decades, the idea of a black hole at the heart of our galaxy was just that, an idea supported by indirect evidence. Then astronomers did something remarkable. They watched individual stars near the center of the Milky Way trace tight loops over many years, orbiting an invisible point.
By tracking their paths, they measured the mass hiding in the dark. About 4 million suns squeezed into a region smaller than our solar system. There is only one known object that fits that description, a black hole called Sagittarius A. In 2019, another milestone arrived. An international collaboration known as the Event Horizon Telescope used a network of radio telescopes spread across the Earth to act as one giant dish the size of our planet. Their target was the supermassive black hole at the center of the galaxy M87. The image they produced went around the world. A glowing ring of hot gas surrounding a dark shadow, the silhouette of the event horizon itself. For the first time, we had seen not just the consequences of a black hole, but its immediate outline against the light. Not long after, the same technique gave us an image of Sagittarius A, our own galactic black hole. There it was, a turbulent, flickering ring of radio emission around a shadow in the heart of the Milky Way. The monster at our center revealed. As if that were not enough, space-time itself began to speak. In 2015, the LIGO observatories detected tiny ripples in the fabric of the universe, gravitational waves, produced when two black holes spiraled together and merged. Since then, dozens of such mergers have been recorded. Each detection is a confirmation that black holes are not exotic fantasies. They are real. They collide, and they shake the universe when they do. And yet, for all this evidence, for all these images and signals, one fact remains unchanged. Every observation we make stops at the same place, outside the horizon. We can map the orbits of stars, the swirl of gas, the ring of light, and the waves of space-time. But what lies beyond that circular shadow, the interior, the singularity, the final fate of matter and information, remains hidden. The universe has shown us the outline of its darkest secrets. The center is still missing.
When you stare long enough at a black hole, you are not just looking at an object, you are looking at a question. What exactly is on the other side of that shadow? Some physicists treat the singularity, that point of infinite density, as a signpost, not a destination. It marks the spot where our current map ends. Replace the equations with a better theory of quantum gravity, they argue, and the singularity may dissolve into something more physical, a region of extremely curved but finite space-time, or a tangle of quantum structures we do not yet have words for. Others speculate more boldly. In some models, what we call a black hole might be connected to something like a white hole, a hypothetical object that can only spit matter and energy out, never let anything in. Put together, they can form a bridge through space-time, a wormhole. In the language of science fiction, a black hole could be an entrance, and somewhere far away or in some other time, there could be an exit. There is another idea even more audacious. Some cosmologists have wondered whether the interior of a black hole might bloom into a new expanding universe unreachable from ours, but with its own space, time, and physical laws. In that picture, every black hole could be the seed of another cosmos. Our own universe, in turn, might have begun inside the collapse of some parent reality we will never see. Are these descriptions correct? At this point, we do not know. They are attempts to push our imagination, guided by equations but not yet anchored by data. Black holes invite this kind of thinking because they sit at the intersection of extremes: strongest gravity, shortest distances, highest densities. If there is a place where the universe keeps its deepest secrets, this is it. Yet, amid all the speculation, there is something very down to earth about black holes too. They help galaxies form and grow. They shape the flow of gas and stars. Their violent outbursts can both ignite and quench the birth of new suns. In that sense, black holes are not just destroyers.
They are architects of structure on the largest scales we know. And on a smaller, human scale, they remind us of something uncomfortable and beautiful. Our knowledge has edges. There are horizons in science just as there are horizons in space, places beyond which we currently cannot see, not because there is nothing there, but because our tools, our theories, or our experiments are not yet strong enough to cross. Black holes mark those frontiers with a kind of cosmic honesty. They are nature saying, "Here, for now, your understanding stops." But the story does not end there. It never has. Once, the edge of knowledge was the sky. Then it was the orbit of the planets. Then the stars. Now it is the darkness around a handful of invisible objects scattered through the universe. Each frontier that seemed absolute in one century became routine in the next. Someday, we may have a theory that explains exactly how information survives in a black hole, what replaces the singularity, and what it really means to cross an event horizon. We may look back at our current confusion the way we now look at medieval maps with dragons drawn in the margins, a mixture of bravery, creativity, and guesswork standing at the border of the unknown. Until then, black holes will continue to do what they do best. They will warp space and time, swallow light, power quasars, ring space-time like a bell when they collide, and quietly challenge us to keep asking better questions. Because in the end, the mystery of black holes is not only about what is inside them, it is also about what is inside us, the part that refuses to accept "you can't know" as a final answer. If this journey to the edge of the universe's dark heart made you think, don't forget to subscribe to Hidden Myst. Leave a like, share this video with someone who loves deep space mysteries, and tell me in the comments what you believe really happens inside a black hole. Thank you for watching, and as always, stay curious.